Hi, welcome. Welcome to SF Big Analytics. My name is TJ. I'm one of the organizers, and I'm very happy to present two interesting talks to you today. Before we get to that, I have a few things I want to say. First of all, I want to give a big thanks to Yelp. So not only do they provide the space and all the food and drinks, but they also do the AV recording and all that good stuff for us. They're a pretty good host, and yeah, they do some good stuff here. If you're interested in working for Yelp, I'm sure they're hiring, so you can find someone to talk to. I do also want to mention a couple upcoming talks we have. So on May 30th, we have a talk, two talks. So the first one is called 5 Stages of Enterprise Jupyter Deployment. And the second talk is Airflow, 2 years in production. So I think those will be interesting. And then also on 6/13, we have 3 talks. One of them is on machine learning workflows in Kubeflow. One of them is called Random Walks in Spark Graphs. And then finally, we have genomics on Google Cloud machine learning engine called DeepSea. So this should be interesting as well. So let me just get right to it. We have 2 talks that are full length today, so I don't want to waste your time too much with me speaking. So let me just go ahead and introduce the first talk. I'm really looking forward to this one for a couple reasons. So first of all, I worked with 2 of the speakers before, so I'm really interested to see what they've been working on in the last couple years at GoPro. And also, my company has made a transition in the last few years to having all of our production and analytics on AWS as well. So it'll be interesting to see if there's anything that I can learn from them that can apply to my job. So the title of their talk is Evolution of GoPro's Data Platform, and the speakers are Chester Chen, David Winters, and Hao Zhou. So let me give the microphone to Chester.
Thank you, TJ. So thank you for coming. So it's kind of strange. I usually host the meetup rather than be the speaker in the meetups. So this happened the second time after 3 years in this meetup. So today we're going to talk about the evolution of our data platform. So myself I'm head of the data science and engineering at GoPro. Previously, I was the director of engineering at Alpine Data Lab, so a machine learning startup. I'm also the organizer for this meetup. Dave Winter is our big data architect in our teams. Previously, has working at Apple, Splice Machines, and other companies. Hao Zhou, he's a senior software engineer at our team, and previously had working at Alpine Data Lab as well as Pivotal. So we had a lot of materials to cover. So some of the stuff we're going to go very quickly because we're going to take a lot of time. So we're going to very briefly talk about the business use cases. And then we're going to divide it into several sections. So one is we're going to talk about our platform, architecture platform transformations. And then we're going to talk about how do we develop our batch Spark framework using a really configure-driven. And then we'll talk about the data democratization, which is mainly focused on 2 areas. One is the data management and the visualization. The other areas is how do we deliver data metrics using Slack. And the last one, we just going to talk about the new stuff we just finished. Not really finished, just finished the initial explorations onto how to do visualization with the machine learning features. So we'll get right to it. So GoPro, as you know, so we have action cameras, we have the drones, and of course we just shot on the drone, but we have all these hardwares and people really love for it. We also has a lot of the softwares that goes with these devices. For example, we have several mobile applications. We have the developer programs. We have subscription programs on the cloud. So there's a desktop applications. So if you see, we have the data coming from the e-commerce, coming from the subscription, coming from desktop, third parties, social medias, and then these data goes out to the other user segmentation, CRMs, digital marketings, and so any product analytics. So there's a whole suite of the things we use, and these are just to kind of briefly go through some of the stuff our team working on. So, for example, we support the product analytics that kind of coming from the mobiles, cameras, plus application CRMs I mentioned before, social medias and cloud media. So there's a whole suite of stuff we're working on. These data could be churn analysis, user segmentations, partitions, and all these different recommendations. And the other teams inside GoPros, and not necessarily my teams, they also working for deep learning using for image qualities, also for recommendations for mobile applications. So there's a lot of cases. So I'm right to, so that very, very quickly, so because we got a lot of stuff, so I'm turning the mic to Dave Winters, going to talk about the architecture changes.
Awesome. Thank you, Chester. Again, I'm Dave Winters, the big data architect within data science and engineering at GoPro. And what I'm going to do is I'm going to kind of walk you through, actually relatively quickly, this actually used to be part of a larger talk, but I'm going to talk a little bit about the evolution of our data platform. So I've been at GoPro going on 3 years, and we've essentially gone through 3 different versions of our data platform. We get performance reviews once a year, so you want that one meaty topic, each year. So starting off in 2015, we started off with essentially a fixed-sized Hadoop cluster. I would call it your traditional data lake. And basically the 3 primary workloads that you see within a data lake or any data platform is going to be your ingestion of the data, your ETL, where you're doing your various transformations, your aggregations, any filtering, pre-joins, and then finally you're going to do what we call data delivery, which is essentially your analytics, being able to have fast scan speed, be able to support all the data scientists and the analysis that they want to do. And so when we, in 2015, came up with that, and it's obviously not very novel, pretty much everybody's doing that, and we ran into several problems. First of all, a poorly written query by a data scientist or an analyst, or even just a heavy query, could bring down essentially the whole cluster, which means your ingestion starts to fall behind, which is a pretty bad thing when you're streaming the data in directly from devices and from mobile applications. And so that really led us to our second version of our data platform, where we separated the ingestion, which we call streaming in this particular section here, from our ETL, which is essentially batch processing, and then separated that from our queries, our data delivery. That worked pretty well, but the next problem we ran into is the fact that all of the clusters were statically sized. So we do have a very cyclical nature to our data at GoPro. Our users tend to take their cameras out on the weekends, tend to be weekend warriors when they go skiing, when they go swimming, mountain biking, you name it. They tend to bring the cameras out on the weekends, which means they're connecting to the mobile applications, they're connecting to the desktop applications, they're connecting to our cloud, and that's when we start to get the analytical logs. And so you see these huge spikes on the weekends, and then throughout the week, it's pretty low. So it's very similar to an e-commerce spike in traffic, for those who are familiar with that. And so it means that for 5 days of the week, you're really barely using the hardware, and then on the weekends, you're really spiking up. Same thing with holidays. GoPro cameras reappear again. People use them on the holidays, and then there's mass purchases of GoPros during December. And so again, you're paying for all this hardware that just sits there. So that's really what led us to our third generation of our platform. And I'm going to actually talk a little bit about that. And then later on, Chester will actually talk about our fourth generation, where we're getting beyond just the data platform and actually getting into a machine learning platform. So let's kind of jump right in here. For those that may have seen some talks that I gave at Spark Summit, along with How, and also at the Hadoop Summit, this is actually a very similar diagram. So this is basically our 2.0 architecture that we had a little over a year ago, about a year and a half ago. And so you'll see the ingestion is here on the left-hand side. You've got the streaming cluster. These are logs that are coming in from our devices, from our mobile applications, desktop applications, and also from our cloud service, GoPro Plus. They tend to be mostly, well, they actually are a variation of different types of log formats. They can be JSON. They can be a proprietary binary format, which is coming from our devices. And what we do is they go through a RESTful web service that we have. We use Kafka to queue them all up, Spark Streaming to process the logs, use HBase to track the state of various entities. And then ultimately, we have some nice normalized JSON that is basically dumped out at the end. Down here on the batch, this tends to be integrations with third parties, ERP systems, CRM systems, you name it, the social network service of the week that marketing wants to integrate with. It can work with RESTful APIs, FTP downloads, S3 syncs, wide variety of data formats, text files, CSVs, XML, JSON, you name it. It's just a good old Java framework. We do the normalization into JSON files, and then again, everything ends up on our ETL cluster. ETL cluster started off tried and true Hive, lots of MapReduce. Over time, it evolved to Spark SQL for most of its processing. Pretty large cluster. It was doing large aggregations and joins. That was on a cadence of several hours to sometimes even once a day, whereas the streaming cluster is anywhere from the seconds to minutes kind of a cadence. So you can see things are kind of slowing down as we go along. Now, the ETL cluster, of course, we did a distributed copy there to get the JSON files from the batch and the streaming clusters into the ETL cluster. Now the files sit there again. We've also converted them to Parquet with gzip compression to improve the scan performance. We've also created DDL at that point, so we've added structure to those files. And then they also sit there for a while. It can be several hours to several times a day. They get copied over to our secure data mart. The secure data mart at that time was on a Cloudera stack, so we were using Impala for the in-memory SQL execution engine. It was secure. We were using Apache Sentry in combination with Kerberos and LDAP. Chill just went down my back thinking of Kerberos, but it did keep it very secure. And then the applications at that time were mostly Hue for SQL access, and then primarily Tableau for the reporting, and then some Plotly that was literally just being run on data scientists' MacBooks. There's a couple of data scientists that were a bit more, I won't say cutting edge, but a bit more aggressive, and they would actually use Python and R directly on their MacBooks. So, it worked, but definitely some improvements we could do. Just want to kind of jump in just a little bit in a little more detail. We'll move on to the 3.0 architecture. This is just a deeper dive into the streaming endpoint. Again, pretty standard stuff as far as like a pool of Tomcat servers here with a custom Java servlet behind an AWS ELB. Everything has been from the beginning in EC2 for us. They would basically accept the logs. Logs would get posted to it. Wide variety of logs, as you can see, binary formats, JSON. Some of them were compressed, some weren't. Those logs, after some basic authentication, are then stuffed into a Kafka topic. A series of Spark streaming jobs pull those logs off. They process them, stick them into another Kafka topic, and it kind of goes round and round for a while, and we'll dive into that in just a second here. At the same time, we would be updating the state of various entities, because again, we're getting event data. We also want to track the state of these entities. We use HBase for that. And then ultimately, you have that nice normalized JSON, which is being dumped into an HDFS cluster, which is part of that streaming cluster. Depending on the schedule of that particular pipeline, it could sit there for minutes or it could sit there for hours, even better part of 8 to 12 hours for some pipelines before a distributed copy to the ETL cluster. This is just taking a little bit deeper dive here in that kind of cyclical relationship you saw between the Kafka topics and the Spark streaming jobs. So what we do is we've created reusable components for our Spark streaming jobs. The first thing that we do is we always handle PII, or these days the popular four-letter acronym is GDPR, which is basically how do you properly handle private data. So we do that from the beginning and manage based on the various rules of the regions, what's get hashed out, what gets removed, and so forth. And then we start routing the logs based on either the type of data or the application or device that it came from. They go down their specific code paths. There might be a path specifically for camera logs. There might be a path specifically for a mobile application. Ultimately, at the very end, if you kind of take a look at that last row of Kafka topics, or last column of Kafka topics, things begin to slow down. The cadence up towards the top of the tree here is more like, well, it's about every 2 seconds. When you get down a little slower, it can be once a minute or even as slow as once every 5 minutes or so. And so we're dealing with that classic Hadoop problem of small files, which is basically a no-no, basically a killer for anything related to big data. So we start to collect up the data, wait till we have a sizable amount of data, and then we do a nice large flush and write it to HDFS. At this point, there are compressed files, LZ4 compressed JSON files, and then they sit on that HDFS cluster, which is part of your streaming cluster, for a determined amount of time, but it's definitely a lengthy amount of time before we copy it over to the ETL cluster. ETL cluster, basically has two inputs from the streaming cluster. You got that nice normalized JSON data that we talked about. You've got the batch induction framework, which is doing downloads, usually from RESTful services, S3 buckets, FTP websites, and so forth. Cadence here could be once a day, could be hourly, just depends on how often that third party provides the data. Again, normalized JSON ends up into an HDFS, a set of directories within our ETL cluster. So we've got two distributed copies here occurring. You've got a Hive job, later a Spark SQL job being kicked off, Parquet files being generated, schema along with those Parquet files being generated. And again, it sits there for a while. We also take snapshots of our HBase database that we have there, where we're basically tracking the state for various entity objects. Same thing, Parquet files and their analogous schema files, or schema, I should say, within the Hive Metastore being stored. Waits there a while. We have a scheduled job that kicks off and then copies that over to our secure data mart, which is essentially how the analysts were accessing data at that point. Pretty straightforward here. This is the secure data mart cluster. You've got Parquet files, you've got Hive Metastore being replicated across. You've got, at that point, as I was saying, Tableau, Hue, and maybe some Python code, which are accessing via ODBC. That's pretty much the primary access mechanism at that point for our platform. And they're creating Tableau reports and extracts, or just custom output files from their Python programs. So definitely some good things we did with our second version of the architecture. Isolated the workloads, isolated the ingestion, isolated ETL, isolated the data delivery. Ingestion was fast, used Spark Streaming, Kafka. We weren't dealing with millisecond latency here. We were dealing at fastest several seconds to minutes, but it was fast enough for what we needed to do. Secure, we used Kerberos with authentication and Active Directory and Apache Sentry. Fast delivery, I would say that, you might want to put air quotes around that, as long as your query fit within the size of our statically sized cluster for the secure data mart. The analysts were happy. And as you all know who've dealt in that field, you can never have a large enough cluster. And of course, whenever you get that cluster that large, then you take a look at it and it's just sitting there for hours being unutilized also. The clusters were loosely coupled, which was nice. You could do some maintenance, say, on the ETL cluster, when in fact the streaming ingestion at all, and vice versa. Of course, areas we could improve: multiple copies of data, 3 copies of data at a minimum. And I'm not even talking about the replication, just talking about 3 different clusters. Tightly coupled storage and compute. So the holidays are rolling around, you're getting ready for that December push. You need more CPU, but you're fine on storage. Well, guess what? Homogeneously sized instances. It's what Hadoop wants, so you're going to be adding extra storage even though you don't need it. Lack of elasticity, very painful to expand. Not too bad. The HDFS shrinking, definitely painful. And then just the operational overhead of dealing with these multiple clusters. There was a lot of, let's just say, testing in production. It was very difficult to replicate these clusters. So with that in mind, we set off on improving this. And this is what we have today. This has been in production actually for probably about 9 months, I'd say now. This is our 3.0 architecture. So when you take a look, you're going to see a lot of similarities. You're going to take a look and you're going to say, well, I see your ingestion on the left-hand side here. Okay, we've got multiple streaming clusters now. Got your batch induction framework down there. Got the ETL clusters. Oh, okay, well, they're ephemeral now, and there's multiple. Same thing over on what used to be our data mart. We've now got multiple analytical clusters. And then you'll even start to see some differences, like, oh, well, geez, there's this Druid thing here, and gosh, it doesn't even have a cluster it's connecting to. So several improvements here. The biggest thing is actually right in the middle of the picture, the centralized data repository. So we have one copy of the data. Everything goes into an S3 bucket. We have one Hive Metastore now. We previously had 3, one for each cluster. We have centralized HBase so that it's accessible by all clusters now. And then we even have Kafka in the middle now. Kafka previously was only used for ingestion. Now we're actually not using it just for ingesting data. We actually use it to publish data. So in this particular case, we actually publish data now to Druid, which is currently under development for us. But Druid works great with consuming messages directly out of Kafka and then creating its cubes and then allowing a UI such as Superset to do visualizations. Once you get everything into one place, one central copy of the data, that automatically, of course, is separating your compute from your storage, which then allows you to have elasticity. So we now have actually many different streaming clusters. They're much smaller clusters versus the one large cluster previously. The ETL clusters, which used to be there, and it was a big old hulking cluster, and it sat there all the time, even though it was only once every 8 hours that we kick off this giant job. It now actually, the clusters appear and disappear as they're needed. So we're not paying for those clusters to sit there all the time, especially now that Amazon and various other service providers are billing by the minute. Definitely saves you a lot of money. And then one of the most important things is we really reduce the DevOps cost. We, like many organizations, don't have a ton of DevOps. And so it's always painful to have to do any reconfiguration of clusters. And definitely when you can create them in an ephemeral nature and you're not dealing with HDFS, it takes a huge amount of DevOps load off of your backs. And so because of that, we've been able to do things such as deploy our data into many different environments now. So we have notebooks, first of all. Huge win for the data scientists. No longer do they have to write their Python or their R code directly on their MacBook. They actually can write it directly into a notebook. Allows data engineers also to use them. We can use Scala directly, which is a very powerful tool. We've been able to integrate Plotly directly with the notebooks. Same kind of thing. So again, they don't have to run Plotly directly on their MacBook to do their viz. They actually can integrate it directly with their notebook. And then we've even been able to open up different ways to push data directly to Slack. We still support Tableau. We still have a very large number of reports that are in production today on Tableau. And for those hardcore developers that still want to go directly write Python and R on their Macs or their Windows PCs, they can still do that, connect via ODBC. So I just wanted to kind of quickly go through and show you the simplification that we've been able to make in all of those different clusters now that we have come to this new elastic cluster architecture. So now when you take a look at the streaming pipeline here, very similar. You got the logs coming in, EOB, the Tomcat servers. You still have the Spark streaming jobs, reading and writing from Kafka topics. But now the difference is we have they're all long-running clusters, but they're essentially ephemeral. So when we need to kick off another pipeline, we want to create another cluster, it's literally just a matter of a few clicks. Makes it so much easier. All of the data now goes directly to S3. We have a centralized Hive Metastore, and then the data is available to every single cluster instantly. Very similarly on the batch jobs here, the ETL jobs, we did change our scheduler. We used to use a commercial product. We did change it to Airflow. To be honest with you, it wasn't a huge change. We kind of use it in the same fashion. But what it does allow is it does allow us to copy the DAGs and create development pipelines very easily. And so the same kind of thing, very simple configuration. You can set up a batch pipeline. Again, it'll spin up a cluster on demand for you. Again, it's writing directly to S3 and Hive. We actually do a lot of pushing now directly to Kafka and even some applications like Slack. But if you're a developer and you want to make some changes, instead of the old days where you do testing in production, essentially, you can literally just make a copy of the configuration, set up another pipeline, point it to a different S3 bucket in your configuration so you don't affect production, and you can do your development with production data. Makes it a lot easier. Lastly, for our data scientists that used to be stuck with one single static secure data mart, now they can use notebooks to their heart content. They can use a long-running cluster that we have, or they can create their own, which is definitely probably one of the biggest wins for us, because previously, it didn't matter how big that cluster was, somebody would come in and they'd be like, oh gosh, you got to really take a look at the last 3 years of data and analyze such and such trend. And they'd kick that query off, and of course, it would bring the cluster to its knees. everybody else's query, even if it was just going to be a very short query, queues up. Now they can create their own on-demand cluster and do their own analysis. Then same thing, just a wider variety of tools that they can use these days because of that. So a couple things, just to kind of wrap things up on the takeaways here. Key changes, as I said, we centralized the Hive Metastore. We've leveraged S3 as our centralized storage. So again, we have a centralized data repository. That allowed us to separate the compute and the storage. Being able to do that allows us to have the cluster elasticity, so you can shrink and grow clusters. You can create as many clusters as you wish, so you get that horizontal scalability. And it really means we spend less time doing DevOps work, which is a great win for definitely all data engineers. Challenges, it wasn't that easy, I will tell you that. This definitely was in the making for quite a while. I'd say two, the big challenges we faced, number one was pushing data to S3. Definitely don't underestimate the challenge there. S3, the great thing though about S3 is you can do very large parallel writes. So you're not going to get a ton of throughput with one single thread, but you can write with many, many threads at once. And it essentially, I mean, I don't want to say it's infinite, obviously everything has its limits, but we've been fortunate we haven't really reached any limits with that one yet. It takes a little bit of tuning, but it definitely is a great way to store your data. The one that was unforeseen to us, and it was one that we kind of missed on a little bit, was when we switched from using a Hadoop distribution to using a cloud service, was the fact that Yarn was no longer available. And even though you kind of think like, well, it's a Spark program. I mean, I wrote it in Spark Core, Spark Streaming, or Spark SQL should just work the same. The deployment is very different. If you're going from a Yarn, I don't have experience with Mesos, so I won't speak to that, but definitely moving from a Yarn to Spark standalone, very different profile. What it really meant was we changed from using these very large EC2 instances in many containers, and for us a container was a JVM. We switched to using many, many small EC2 instances. We also had to combine a lot of I'd say our low throughput Spark streaming jobs in order to fully utilize the CPU on those systems and the I/O. We were just wasting money, so we did combine a lot of Spark streaming jobs. And it's definitely, we will be considering a move to containers, probably a Kerberos or something similar in the future, so that we can stack more containers on EC2 instances, and again, just utilize those machines a little bit better, get a little better cost effectiveness. But speaking of cost effectiveness, this is kind of the major slide, is what they always like to see. The cost, we reduced greatly the redundant storage, obviously. We were paying Amazon a lot of money for EBS volumes. Definitely reduced the compute cost also. Using smaller instant types, saved us quite a bit of money. Overall, 60% cost savings from a year ago. So we were definitely really happy with that. Operationally, we reduced the complexity of the DevOps support dramatically, where there really isn't much cluster management that has to occur anymore. And then finally, the data scientists were quite happy because they went from pretty much only having SQL access to having full notebook abilities, support for SQL, Python, Scala, and even R. So with that, I'll hand it over to Hal, and he's going to walk us through the batch and ingestion framework.
Thanks, David. My name is Hao. So I joined GoPro for about 2 years, I guess, and mainly helped the team transforming our data platform from 2.0 to 3.0 and building the patch framework and as well as our data management self-service also. So now I'm going to talk about our batch ingestion framework. Oh, sorry. So before we really have this batch ingestion framework, what we used to do for the batch ingestion is we writing some Spark job, or even before Spark, we write some MapReduce job and compile the code and ship the jar to the production, then run the jar in production, which is a little messed up because some people maintain the job will leave the company. So if they leave the company, then we don't know how to maintain the jar that they build. So that's why we think of building a centralized batch framework, which has a centralized configuration with code-free configuration, and people can just make the configuration, then run the job from there. So yeah, So this is our batch ingestion process, and basically there's as normal we have like a batch data download, which will download data from SFTP or REST API or S3. And as David said, we have a streaming pipeline. So basically we will have some data from streaming pipeline and go to S3 as well. And also we have an Apache HBase to persist some state data. So we also want to ingest some data from HBase to our Hive warehouse. And recently, we have a request from media team. So they have a Postgres database. They want us to ingest their data into the Hive warehouse to help the analytics to analyze the data. So this is our batch framework mainly support these three sources. One is from the file, one is from the HBase, and the other is from the Postgres database. But it's all going into the Hive warehouse. So this is our batch job. Basically, this is all our supported batch job. So basically, we centralize all our batch processing into a single framework. So we have like Spark job at top, which is the interface. So every job will inherit from there. And we have the Hive table writer. As I said, we only have Hive warehouse. So all our data will be finally input into our Hive. And this Hive table writer will support the dynamic DDL. Like David said, we automatically detect the column changes and change the table, change the destination table. So basically, no matter the incoming data has their column change, we will detect automatically. And like I said in previous slide, we have three main sources. One is from file to Hive table writer. One is from HBase to Hive table. The other one is from table to table. And we mainly support CSV and JSON in our framework because this is what we need. But we can grow when there is a new data format. And the HBase table is mainly for a snapshot because we keep the state, so we need a snapshot of the data. We ingest a snapshot into our Hive table. And the table to Hive table writer mainly consists of JDBC to Hive table writer and table snapshot, and also some aggregation job because sometimes you want to create a derived table from Hive table. So as I said, this is a code-free process. Basically, we already have all that set up. So whenever there's a new request to ingest data, we only need to add a new configuration. We don't need to write code. So this is like a sample configuration looks like. So the job type, which is the ETL in this way, and the job name, and the conf part, which we have some Hadoop configuration because we're running our jobs on Hadoop ecosystem. So this will be some Hadoop configuration and a Spark configuration. And the process is we have basically defined which class you want to use. You want to ingest a file to Hive table writer, or you want to ingest a HBase table, or you want to ingest a table to Hive table. And the input will be the input path or input database and the table. The output will be the final output table and the final output database. And the post process will have some like whether you want to keep the input source or you want to archive the input source. So this slide will have like a detailed sample of the configuration. So as you can see, the input will have the input directory and the input format. And also, because this is CSV, so you can define the parameter and all the other stuff. And the output will be the output database, the output format, and if you want to have a compression, you can configure the compression there. And here, the post process, we define, okay, we don't want to keep the source, we want to delete. So with this ETL batch framework, currently we don't need to write code for most of the time because our framework currently supports all of our needs. Whenever there's like a new request comes in, we just go to the configuration, then add a new job there. And we don't need to deploy the code because we don't change the code. Then the job will automatically, we will like schedule an Airflow job, the job will run on the Spark cluster. But this is only like an ingestion part. Sometimes we want to like transform the data. We want to transform the data from the base table to some derived table. Then our framework will also support some general SQL transformation. And you can also run some Scala to transform the table to table. So we mainly support these three kinds of three ways to transform the table. One is through the Spark SQL. Basically, we will have a JDBC protocol to upload your SQL to the Spark cluster and then run the SQL there. And the other one is the Spark job. So if we want to use Spark job, we have to recompile the code because you need to add the Spark job in your code, then add the configuration, and recompile the jar and ship the jar, which we don't want to do. That's why we come up with this Scala script. With this dynamic Scala script, we write the Scala script, and the framework will automatically compile the Scala code at the runtime and run the logic there. So I'm going to show you guys a Scala script example. So basically, you define a class which extends the Spark job. Then you override the run method, which define your logic there. Then at last, you return this job back. So our framework will pick up will evaluate this file and compile the code at the runtime, then run the logic in the run method. In this way, we don't need to compile our code, basically recompile code and shape the jar. We just change the script, then shape it, then the framework will upload the script to the framework to the Spark cluster, then run the logic there, which save us a tons of time, because if you recompile the jar and wait the Jenkins to build the jar, it takes like 2 or 3 hours, and you have to wait other people to approve you to redeploy the jar in the Spark cluster. So basically, this is our batch framework. But sometimes we want to like monitor our framework. We want to monitor our pipeline, and sometimes we want the analytics want to visualize their data, and sometimes they don't want. Even our framework is free code. They don't even want to modify the configuration. They only want to have like a UI that they can upload some small file there to our Hive warehouse and preview there. So that's why we comes up with this visualization and data management web portal. So we build like a web interface. We are using React in the front end, basically to build like a web UI to help them to do some self-ingestion and data visualization. So currently, our self-service portal contains these 5 services. One is pipeline monitoring, one is data management, and also product analytics visualization. And for this, I think we don't have too much, but we are working on that. And the self-service ingestion, currently we only support some small file ingestion. For the large file, we build the backend, but for the front end, we haven't have some time to do that. But we are continuing working on that. And we also have some other tool services, like our brand protection team. They are using our tool to detect the fraud. So I'm gonna do a demo here to you guys to give you guys like understand of what is our web service portal looks like. Sorry. So this is our backend basically our backend will contain the documentation of our API. So I'm not gonna show you details of this this API. So I'm gonna show you the what the front end looks like. So basically, our front end will contain these several services. So we have a warehouse, which is this is like a purely data management, which will have like show you what is your Hive table looks like. Basically, you can upload file into this table. You can preview the table. Something it's like something like this. So yeah, so this is mainly for analytics to like look at some sample data, and they can upload their data. Sorry, not sure it's good. And okay, this is fine. So. There's already okay, that's fine. So it's a little awkward here, but anyway, so this is the idea. So basically, we provide there a way to do this data management, and also we give them access to our S3 bucket. They can upload file there. And for the services, we have this self ingestion, which we haven't done yet, but we will continue working on that. And for the monitoring, so we have some pipeline monitoring, which will basically they will tell us whether our pipeline works or not. So a couple of our monitoring looks like, and we have some other tools which our brand protection mainly include their camera serial number, and they will give them some result whether the camera serial number is fraud or not. Yeah, I think that's it, pretty much it. And in the future, we probably want to add some machine learning on this web portal. I will hand over to Chester to talk more about that.
Thanks, Al. Yeah, so we are very early in the stage of this data management platforms and the visualization. What you see here is just the very, very beginning, what are we trying to build there. So we have a lot of visualization stuff we didn't get a chance to incorporate it before today's meetup. So we really want to show you maybe down the road. One thing I want to point it out is he said it's legal teams using our services to do, against the fraud against GoPro. We actually save about over $4 billion just to use that tool. So it's the service is really useful for GoPro. So let's continue our talk here. Okay, so we are in 2018. So this is the areas we are currently focused on. That how do we get the data to the more hands, the data that we collected in a useful data to distribute it to more users, the product managers, engineering managers, and the analysts. And then how do we go to the next steps besides the visualization data management, and to how do we transform to the machine learning platform? So again, we're in the early stage. So what are we going to talk about? There's two parts. One part is how do we deliver the data metrics to bigger audiences. So so one thing we did is actually we're using Slack. Sorry, I masked all the numbers there. Just give you samples what it looks like. So so we're using Slack to give metrics to the product owners, the engineering managers, product managers, and analysts to see what's the high levels our business doing. So we've done this for our subscriptions, for mobiles, for our cloud medias, and many other channels. And so these are the private channels. So so you probably ask and say, why are you doing this? Why you're you're not using Tableaus or using other services. Why are you using Slack? So what we find out is, for example, Tableaus. Our data analysts actually, some of the data analysts actually put a huge business logic in the Tableau SQLs. So there create two problems. One is that all the logic, the business logic, is directly embedded in that SQL. And when he or he leaves the company, nobody understands that stuff. So and it was hard to maintain. And then the data, the SQL itself is not go through the engineering process. So nobody quality checking that. And then essentially when he leaves, that whole thing had to start over again. So that's one problem. Second problem is usually the people who are writing this don't consider the big data problem. So essentially, okay, I will collect all the data and then I'll do visualize here. So that data is collecting from the big data to come to Tableau is huge. So take a long time and keep broken and all that stuff. So that's one of the issues we've seen. So what we want to do is essentially for some of the data, we actually want to, some of this aggregate data we want to bring in to our software discipline so we can, these data is pretty much very simple SQLs most of the part. And if this need a complicated SQLs, we can build aggregation tables and then build on top of that. So we leave the analysts to do more user insights, more deep analysis. And so these are things that we can actually do by the engineering data engineers. So okay, in that case, why Slack? Why not other tools? So what it turned out is the Slack is very easy to get to. So if you push to it, and you usually easily get it. So the one thing is that people say, oh, you give me a URL, so I have to log in and all the other stuff. So this one is if you connect to Slack, you already log in. So you look at the channel, it's right there. All the data in private channel is invitation only, so it's not like everybody can see your data. It's only the business owners care about that particular places that you invited. So as I mentioned that the SQL code is under software controls, where we publish in the data on the schedules and we monitor the performance. If something takes longer, and then we can go there to modify it. And then on the other thing is, once the data is published, sometimes hey, wait a minute, that number get a spike. That's not right. And it doesn't seem to make sense, the number. So the discussion in comments right there in the channel, and the people started discussing, find out the issues. Why all of a sudden there's a spike? Oh, some service provider did something, and suddenly we got X number of million users or whatever. So those are quickly become a discussion point. So what we want to do is using Slack and essentially a configuration driven. So all the multiple private channels, and then we use a weekly, daily, weekly, monthly delivery and a comparison. As you see that in the quickly just go back here again. So this essentially we publish two numbers of most cases. You get one numbers for this week or this month, and then the previous week's number, and then the percentage changes. So you can up and down all that stuff. So and then depends on the business needs. We'll also have these graphs. These graphs could go to multiple weeks or multiple months and see the trend at that point. So again, so here is the channels usually have multiple metric groups. This group could be you have multiple mobile applications that go to the same channels, and each groups have multiple metrics, and each metrics have these three queries, and everything is just simple queries. If you just want to see the current number, no comparison, sure. It's just one query. If you need a comparison, you put a comparison query, and if you didn't chart it, put a chart query. So essentially, all the data will be, get plotted. And then these data optionally be persisted in the Hive tables. So you want to go back to say, hey, I want to see all these metrics for the last year, so I can do seasonality analysis and all the other stuff. You can go back to do that. And in addition, as Dave mentioned, that we actually start to pushing these data into Kafka, and then it will be consumed by the Druid and also the new superset visualization tool we have. So it's kind of an architecture that looks like this. So the pushing to Slack is trivially simple because the Slack has this webhook, essentially expose you to a URL, and all you need is just do a HTTP post to it. And then in our case, we basically writing a Spark job to generate the data. So the data is essentially Spark job running against the Hive, generate the metrics. But the graph part is a little tricky. So because we send the data to the JSON files, configuration files, to our REST API servers, which Hal showed earlier. there we use the poly to generate the graph, and the graph is coming back saved to the S3. And then when we display the graph on the Slack, it's actually pulled from the REST API server, and which loaded it from the S3. So that's kind of the overall flows. So okay, so say we did that. We had quite a success. Actually, we have multiple channels. Over 100 people started engaging in our metrics, and of course these are high-level matrices, and we quickly deliver all the executives and all that stuff, and they basically people watching this on a daily basis. The issue with this with Slack is that there's really not much real estate to play with. Literally, you have 2 columns. If you have 3 columns, the whole thing just so it's not really good for really detailed analysis, but it's a high-level metrics. That's very important. So one thing we were thinking doing, we haven't really started implementing, is basically on one of these metrics, we put a hyperlink there, and that link to superset. Essentially, if you want to additional graph and analysis and more details, you can go there. So that's kind of our implementations. So switching gears, we're going to talk about this initial explorations in terms of our transition to the next phase of our platforms. How do we build the machine learning infrastructures? So the first part is, so if you see the timelines, we are still here in this, but we're moving to the machine learning side. So the thing is, so if you build a machine learning, so you say, okay, there's a general different problems. What framework are you using? Do I use the traditional machine learning, deep learning, and how do I control the version control, the source code, whether you can reproduce the model, how you can version control the models, how to deploy models. There's a standard of, but before you do that, there's also a huge debate in terms of do I need to build a feature store? So if you build a feature store, where do you save them? And last week I had a conference at AI Next Conference. We have a huge discussions among different companies, whether it's coming from Twitter's, Intuit, and Netflix. And we have a lot of discussions that Uber talk about how to, where we store them. So we haven't really figured out exactly how we want to build that part yet. But one thing is we say, we want to, regardless of where we store them, we want to visualize the features. So there's one project by Google called Google Facet. If you're there, they just open sourced this project last year. I think I forgot if it's July or November. So there's 2 sub projects. One is overview. The other one is Facet dive. And both features are pretty cool. I welcome to check. So this talk we're gonna just talk about the Facet overview files and see what we did with it. So what is a Facet overview? So essentially, this is totally copy from the Google's page. You can go to the web page to look at it. So it takes input features for any numbers of data sets, whether it's validation test, training data sets. So you're looking feature by features, and then just looking each cases and see that the distribution statistics and all that. And then you can find out the unexpected feature values, missing values, and whether it's a training and serving screws and test, training test validation screws and all that stuff. You can find the keys abstract. So you can look at that all together. So what does it look like visually? It's like this. So this is examples directly from their webpage. So essentially, they're here looking at 2 data sets. One is a training data set, which is a blue color, and the other one is a brownish color, is a test data set. So you're looking at the different features. You can see the counts, missing, statistics like a mean, standard deviation, zeros, and all that stuff. And you have the distribution on the sites. Okay, so this is all good. So if you look at the information about the overview, Facet overview, essentially there's the implementation consists of 3 pieces. One piece is there's a Protobuf definition about the feature statistics. The second part is how do you generate the stat. The third piece is visualization. The visualizations is Google wrote this implementing the Polymer and then with a TypeScript code. And then this can be embedded into either a notebook, Jupyter Notebook, or a web pages. As far as the feature generations, they did 2 implementations. One is in the Python, so using NumPy, Pandas, and to generate that. And the other one is using JavaScript. And because of these, one JavaScript and Python, both are generating the stats right in the browser. So because the one is in the notebook and the other one is both on the browser. So the data cannot be too large. So if you look at the graph, it looks like this. So these are blue colors, the definition, and then on the left side, the gray side, so you have these files coming, CSV, JSON, whatever. So these are data files. They load it into data frames using Panda. And then the other one is a TensorFlow, and they basically have a code to load it in this kind of a data set. They call it data set entries. From there, you generate use NumPy to generate the stats. And then finally you create that Protobuf in serialization, and you can load it in Jupyter to look on the right-hand side. So that's kind of one implementation. The other side is the same definition. You can use a JavaScript to generate the code and generate the stat generator and produce the same Protobuf, and then you create the visualization on the other hand. So for what do we do to say, hey, wait a minute, so this doesn't work for the data that I'm working for, most on Spark and big data. So what if I basically generate this data frame instead of using Panda? I'm just using Spark. So this is what we did. Essentially, this is so it's possible to generate the larger data sets with a small data, it's possible to generate a large data set, but a small, the Protobuf for a stats file size. Can we generate leveraging the Spark distributions and distributed computing capabilities? So can we generate one, instead of having two implementation, can we generate one Protobuf of data and use for all cases? Whether it's Jupyter's or web pages. So that's kind of, if you look at the graph, essentially what we did this. So we have the Protobuf definitions. We can use the Scala Protobuf. It is the open source projects. Can generate the Scala Protobuf code, just like the other pieces together. And then we're using Spark to load the data into a data frame, and then basically generate the stats over there. And then we produce the same Protobuf, and then it can be fitted into two places. Of course, by doing this, Spark doesn't support the TensorFlow files, and so basically we cannot do the TensorFlow part. But that's a separate part of this is the pieces that we're currently implementing. So what we have is actually quite simple. So basically, this is the kind of a sample code. The Python implementation essentially just using dictionaries. So basically, a key value like a map, you get key value pairs. So we put some structures around it with some case classes in this case, like for example, name data frames, which is training test and all that stuff. And then here's the code is very simple. You load a CSV files, and that's just a function like leveraging the Spark CSV loader to load the CSV files. You put a feature there, and you load the two data frames, and then you set the columns, essentially features, to a trained data set. And then you create this list of data frames. You created this feature stats generators, and then you just say Protobuf from the data set, and then you got a Protobuf. And then after that, it's a persist the Protobuf, essentially just save the data to a file. So that's it's a pretty simple. So the signatures look like this. The definitions. This is very similar to the Python definition. Essentially, you have a list of named data sets. Plus, if you specify the feature set, that's only generating the feature for the given set. If you, like the example I have is, I didn't specify that we should generate everything. And then the other one just shows how much histogram levels you want to generate. So that's the case. So, what exactly it looks like when you write the code. So this is essentially what it, in this case, is for example, I already have this stats. Right, so we're basically saying, okay, I load that file and I read it into just read the file directly. And then it was in this case, it's basically I'm reading directly into a binary Protobuf files, and then I need to go to the same thing as basically base64 encoding and all other stuff. You get a string, and then directly using HTML templates and put the string there. And voila, you show the same thing here. So I'm going to actually do a demo. I don't know how much time I have. Oh, we are probably over on time, right? I'm going to go very quick. All right, so I'm going to have to do quickly because I run out of time. So the first one is Google's original example. So essentially, I don't know, you can see the font is pretty small. So the first part is just really, the first part is just some imports, and the second part is the second cell essentially loading the CSVs into data frames using pandas. And the third one is generate the stats, and the last one is display the stuff. And I'm going to just quickly run. So this is the Google's the original data. So you can see the different data sets and all that stuff. So I'm going to quickly run the new one. So in this case, basically I'm loading the file directly from the Protobuf already generated, and then this is a base64 encoded rather than just an original binary, and I'm going to show you the data. So the first, I'm going to do the same data set as the Google did. So now you see this, you see almost identical, except you notice that in the Google side is we have integer in the string, essentially the two data types, mirror type and the category types. Here I actually got three, the integer, flow, and the string. That's due to the Spark loading the data frame slightly differently. The rest of the stuff is the same. So now I'm going to load our own data instead of Google data. You see this the our I just pick a few features from one of our tables, and basically these are GoPro cameras, some of the camera table stuff, and so you can see the same thing. So you can see this is from the Python for Jupyter. We can load our own data. So the next one I'm going to show quickly on the same file, it's exactly the same file. We can load it in the web, not the Jupyter, but it's only. Oh, sorry. As you can see that exactly the same files are showed on the web page, and this is not a Jupyter. So this is a kind of I think I run out of time, so I'm just going to fly through the last few slides and quickly. Oh, well, I'm just going to tell you what it is. So basically, we are very early in this in our exploration of our machine learning platform. So there will have a lot of issues, especially this. This is even though it's working. But basically, we have an issue like, for example, the implementation is not really efficient because it's looking for every features, and some of the data set is produced. The Protobuf files is really large, so it may not be suitable for loading directly into the browser. So we're looking how to put this in productions, and so as we're building up our future stores. So overall, we just moving along. So we're just on our early attempt. So I'll share the experience with you. Thank you so much.
We are running a little bit over, so let's just take 2 questions, and then the speakers will be available afterwards for more conversation. So any questions?
So you showed Google Facets. How do you think Facets compares to something like Trifacta or Alteryx?
I haven't tried the other tools, frankly, so I'm not quite sure. So I don't know how to compare them.
One more question? Okay, I don't see any hands, so let's thank our speakers again. Okay, our second talk is called Detecting Cancer with Deep Learning. And well, we all know data scientists usually just try to sell more ads or more products, get more clicks on a web page. That's what I do at my job. It's always nice to hear about using data science to help the world somehow. And so we're going to learn about detecting cancer using deep learning. So our speaker is Mike Dusenberry, and he is from IBM Center for Open Source Data and AI Technologies.
Thank you, TJ. So once again, my name is Mike, and I work on machine learning at the IBM Code lab. I will just call it Code because it's kind of a mouthful. And just do the obligatory kind of early intro slide on it. So Center for Open Data and open source data and AI technologies. We started in 2015. We were originally called the Spark Technology Center, and we've kind of expanded that more recently to kind of focus or to showcase our focus more so on machine learning. So in general, we focus on machine learning and distributed computing. So we're interested in algorithms for machine learning, applications for machine learning, also just general distributed computing, so very heavy into Spark as well. More generally, we're an open source group, and we're part of kind of a larger open source organization within IBM. And so kind of part of that, we do try to contribute most everything we do into open source. So this entire talk, all the code for it is open source, and you'll see links throughout the talk to it. So if you're interested in running the code or helping work on this project, please, we'd love that. But in general, that's what we are. So 2 goals for this talk. 1, brief introduction to machine learning. So there might be kind of experts already here, but just to ensure that we're all kind of on the same page about it, we'll kind of briefly talk about that and get to some level of understanding, and we'll spend the rest of the time on this problem of mitosis detection. Okay? So first off, what is machine learning? So there's various kind of definitions for it, and I think one thing I like is to say that the basic premise for machine learning is that we've observed some process or phenomenon in the real world, some interesting problem, and we'd like to be able to write down a formula for that process. And if that formula is unknown and it's proving difficult to derive, the machine learning can give you a mathematical approach to be able to approximate that unknown formula based solely on the observations of this process. So if it's easy to observe, but you didn't know the formula and you'd like to, machine learning can help in that sense. And so if we go to like a more broad kind of idea, understanding here, you have inputs, you have outputs, those are your observations. There's some unknown function that maps from those inputs to outputs. We'd like to know that. And so by using machine learning, we can create some kind of template mathematical function in the middle. And that mathematical function can have some number of parameters that will initially start as just random. And we'll learn those parameters such that this function that we're using will slowly start to map those inputs that we've observed to the outputs that we've observed, right? And that's machine learning. And this could be one possible definition of machine learning. And this is very broad in general, but I think this kind of covers a wide range of use cases, and certainly our use case where we'll say that we have images of mitoses, which we'll talk about here, and the output is whether or not, or images of cellular tissue, and the output is whether or not a certain location has a mitosis. So once again, we can learn those. And so I think if we go a little bit more formal, which we won't discuss very deeply, one thing I like to think about is that there are various branches of mathematics that can help to define machine learning and various things. So 3 that come to mind immediately are linear algebra, calculus, and probability theory. And so I think for these, and we don't have to go into it in depth or anything, but linear algebra kind of gives you a very nice mathematical language, in general mathematics as well, to describe these functions, these kind of template functions that we'll create and start from random, and then we'll slowly learn. So linear algebra kind of gives us a language, or a nice succinct language to be able to define those. Calculus, specifically the derivatives in that area, gives us a nice language for being able to optimize these functions. So we start these functions out with random parameters, and we want to learn those parameters. And one way to learn those parameters is to compute derivatives of some type of loss function we'll talk about, and be able to update these parameters. And so we won't go into it, but nonetheless, calculus can kind of give you a nice mathematical language to describe that process versus kind of coming up with heuristics. And finally, probability theory. And so probability theory is a great branch of mathematics that can help define the actual training algorithm and prediction algorithms, and help us actually define what we're trying to do. And on that last point, we had that general thought before of inputs to outputs. But if we take it more formally, we can then use probability theory. We can define different types of problems. And so I'm going to put up two different ones up here. On the left, we have the idea of density estimation. So we haven't observed inputs and outputs, but just a set of inputs. So we'd just like to understand a little bit about that data. So we could think about clustering or trying to understand what's the mean of this data or what's the standard deviation or something more specific. We just have a single set of values, x, and by forming a probability distribution and defining it that way, we now have a great succinct way to define that problem. Won't go into any more details about that, but nonetheless, just an example of using math to define your problems very nicely if you want to go further into this field. And on the right, we have a different problem. And so we could say if we have outputs and we have some type of inputs, we can succinctly describe that problem. We had that nice graph for before by forming a probability distribution of your outputs y with respect to inputs x, or conditioned on inputs x. So once again, just the point being that machine learning is this very nice intuitive understanding that can take you very far. And if you're interested, you can go further into some of the math and help you define your problems very nicely. So nonetheless, that's just a brief thing. And then the last other thing I want to touch on before we kind of jump into the bulk of the talk on mitosis detection is this idea that machine learning is science. And specifically when we think about science and scientific method, right, we identify some type of idea or problem that we're interested in. And based on that, we'll come up with some hypotheses that we'd like to test. And we'll design some kind of experiments. And then we'll run those experiments and we'll evaluate them, and then we'll iterate upon our hypotheses and our experiments over time until we reach like some level of what we'd like to consider success. And so I think that's a great thing to keep in mind, is this idea of science. And while we won't go into it here, but I did talk about more at a previous lightning talk for this meetup, I think experimentation workflows are an important concept to think about and to have a process in place if you're interested in working on machine learning problems. And particularly, we won't go into this right now. Feel free, we can talk about it later in terms of questions or afterward. But I think in general, if you're going to support that process of coming up with hypotheses and then designing experiments and iterate upon them, you need to have some way to keep track of those experiments and to understand why you're running a certain experiment, what happened when you ran that experiment, what's running currently. If you have a multi-day experiment and you're launching a few different ones and you come back in 4 days, you'd like to know why did you run that and what's running. And so having some kind of lab notebook for that, having some kind of setup where you can easily go from running like proof of concepts on a laptop to running on a more powerful server setup, and kind of having that process in place so there's very little friction when you go to work on a real problem is very important. So personally, I use a laptop, and I do have a way to quickly push data and files and code and other such things to a GPU-enabled server so that I can work more on certain problems. And then finally, I think a big piece is being able to evaluate your experiments. So like we said, we'd like to be able to track those experiments and write down the results. We'd also like to be able to see those. And so having some way, and on the right, you'll see an example of TensorBoard, which is one such way to showcase or evaluate ongoing experiments or past experiments. But in general, being able to have some type of metrics that you've tracked and then compare them between different experiments and different hypotheses that you're testing. So overall, you have the brief introduction to machine learning that in general we'd like to be observing some process, we'd like to understand it, we don't understand the formula, but we can observe. And so if we can observe it, machine learning will give us a very nice mathematical approach to approximating that. And then we just remember that more math can help us define these problems, and then machine learning is science. Okay, so now that we're all experts at machine learning, let's talk about this interesting problem of mitosis detection. Finally. All right, so in the picture on the right, you'll see a piece of breast tumor tissue that's been sliced up and placed under a microscope. And prior to being placed under a microscope, it'll be stained with a certain agent that will highlight certain cellular structures of interest. And a physician would look at this, and particularly a pathologist in this case, will look at this piece of tissue, and their goal will be able to identify the severity of this tumor. And one task towards identifying the severity is to identify and count the number of cellular mitoses in the piece of tissue. And a cellular mitosis in this context is the process of cells undergoing division or otherwise growing. And so the intuitive idea here is that all tissue in your body is growing. So all tissue has cells undergoing mitosis or splitting. But a tumor, one of the characteristics is that it grows more rapidly. And so having a count of the number of mitoses could be very helpful towards identifying the severity of that piece of tissue. And so for breast tumors, there is already a standard that given a certain area in terms of space of a piece of tissue and a certain count, you'll have a clear understanding of what the score is. And there's a score 1, 2, or 3. But nonetheless, if we look for a certain cellular mitosis in this example, the little tiny circle on the right, which we can see enlarged, is an example of a cellular mitosis. So a big piece of tissue, very, very small piece is that mitosis. And if you look very closely, of course, you can see the other two up there as well. And so naturally, there's issues of subjectivity. And this is not looking from the outside in, but within the pathology community, they recognize that this is not a very objective part of the analysis. And multiple experts may, in certain cases, differ in their opinion on a piece of tissue. And so the challenge here is, can you develop an algorithm to automatically detect mitoses from a piece of H&E stained tissue, where you've observed this piece of tissue and you've gathered where the mitoses are as a consensus from multiple experts. So you're trying to get a very good data set that's perhaps more objective than you might get from a single pathologist in practice. And then can use that, develop an algorithm, and then have that aid the physician with a more objective algorithm or more objective reading of this piece of tissue. So perhaps you could use that and either supplement the physician's understanding or be able to run it on more tissue, or just act as a backup to the physician. Okay. So given that, we have a challenge data set. And so this came from a challenge that started in 2016. It was called the Tumor Proliferation Assessment Challenge, 2PAC for short. And like I said, that was the goal for the challenge, was to make a more objective data set that could lead to more objective algorithms for that. And for us working on it, we're quite interested in approaching a problem with this data set and trying to replicate it in open source. So a little bit about the data itself. We won't go into too much specifics, but we have about 656 images of tumor tissue. So those tumor tissues are like the images you see on the left or like we previously saw on the right. We would call these one high-powered field, which is more specific, but you can imagine that roughly this would be what you would see if you took a microscope and zoomed in to the appropriate magnification level. So that's about 2,000 by 2,000 pixels. If we think roughly, iPhone maybe shoots 2,000 or 3,000 pixels by 3,000 pixels, so fairly large image, whereas a lot of deep learning-based image tasks are about 200 by 200 pixels. Otherwise, we have some images that are 8 high-powered fields. They're H&E stained. That's just the type of stain that gives it the nice, vibrant pink and blue colors, which are staining various aspects of the cellular structure, which aids the physician in understanding what they're looking at. Magnifications, 40x, and they're saved in a TIFF format. So not JPEG, but TIFF, but nonetheless, they're in a normal image format for us to process. And label-wise, if we have this big piece of tissue, we'll have a CSV file with XY coordinates of the centers of each mitosis. So there could be one, many, or none in a given image, and we'll have those coordinates just of the center. There exists other data sets that have the entire mitosis segmented, but for this particular one, we have the center. And like we said, and this is important, they are annotated by a consensus of multiple pathologists, which is kind to fix the problem temporarily of having subjectivity. So they got multiple pathologists together and made them agree upon what they believed to be the coordinates of these mitoses for this data set. So that way we're training on good data, because if we train on poor data, we'll have the same problems as a physician and possibly worse. So to summarize that, large images, very small cells. Downsizing is difficult. A lot of techniques that we typically use are perhaps difficult, whereas if you think of a lot of types of problems, and especially the ImageNet data set, if you're familiar with that, where you have images of cats and dogs and vehicles and buildings. If you take a big image of a cat and you scale it down to appropriate size that we can actually process, it probably still looks like a cat. But in this case, if you take a very, very small piece, a very, very small cell in the corner or in the center or somewhere, and you downsize the whole thing, that very small cell may end up being like 1 or 2 pixels. So it may be very difficult to actually even see it if you just downsize the whole piece of tissue. So it poses some problems that we'll try to think about and will be applicable to our approach. So before we get to the approach, important part is, well, what's our criteria? What are we trying to actually achieve here in terms of metrics of success? So there are different possible ones you could go for this particular challenge and this type of problem. They're going for an F1 score. And F1 score here is a harmonic mean of sensitivity or recall, depending on terminology, and positive predictive value or precision. So basically, you'd like to catch all of the mitoses. You can't say that every single location in the image is a mitosis or it's useless. And likewise, you also can't say that none of it's mitosis, because that's also useless. So try to catch all of them, but don't just say everything is mitosis. And that's essentially what maximizing the F1 score would give you. They give us a little bit of leeway, and this is more specific, but in terms of positive cases, if you're within some diameter of a given center, they'll count that as correct. But any other prediction anywhere else that's not close to a true center that you've observed is a false positive. So if you get a cluster of predictions that are not near one, every one of those predictions will be incorrect. So it's an interesting thing that will come up. So even though we get a little bit of leeway for positive cases, we get none for incorrect ones. And the idea, though, is if you make a single incorrect prediction anywhere, that's incorrect, and that will affect the final prediction. So how can we approach it? So this is the fun part. So first off, literature. So if we look this up, this type of problem has been thought about some in the past. And particularly, there's a paper from Selfservice et al., which is out of Schmidhuber's lab, a fantastic deep learning researcher. And there's also a paper from Pang et al. The first paper came out in 2013, I believe. And it was on an earlier data set, but they had a similar type of problem, mitosis detection, slightly different data set, but nonetheless, very heavily will be a basis for our approach. The second paper was actually the paper that won the challenge for which this data set was derived. And we'll talk about the approaches. So here's the fun slide. So this is the slide that we're going to kind of break down and go through for the rest of the talk. And the kind of goal here is, what does it look like to actually work on a real problem? So we already talked about what the problem is. We talked about the data set itself. We talked about why we're working on it. So now it's for the algorithmic approach. So to give kind of a high-level overview, and then we'll break it down, and we'll come back to each piece. We start with, let's see, maybe I can't move the mouse. Okay, so we start in the upper left with what we call whole slide images. We won't do it for this particular case, but I think this is medically relevant in that that's what the piece of tissue actually looks like when you fully sliced it up. So the pink and blue part in the center is that piece of tissue laying on a plastic slide, and anything white and other stuff is just the background. We have the data set, the next one to the right, which is the high-powered fields, and which is basically where they've taken out nice square regions out of that piece of tissue for us, so it's nice and clean, or relatively clean. So nonetheless, it's just medically relevant. That's where that data comes from. So overall, our approach right now that we're trying, and there are other approaches you could take, which we'll discuss, but these are based on the two papers with a little extra stuff, is to take those high-powered fields, cut them up into smaller patches. So we can't probably downsize, but we could possibly cut them into patches, patches of some size that we could actually process or that are more normal size for the types of algorithms we'd like to run. Then we will train a model. So we'll do some kind of perhaps either pre-trained model, which we'll talk about, or our own custom model. We'll use some type of augmentation probably during training, which is very common, which we'll talk about. And then we will make predictions. We may go back in with our model and recreate a better patches data set because we'll find that we can't generate every possible patch location just based on the amount of data. And it's more likely that we will not get difficult patches on the first round. So when we go back in, we'll be able to get more difficult patches, which we'll talk about. Given that, and we kind of do that until we feel comfortable, then comes this prediction part of the algorithm, in which case we can make predictions. We could possibly, if we augment during training, we can marginalize during prediction times, which is the corollary or opposite of augmentation, which we'll talk about. And we can come out, we can do some extra post-processing on our predictions, and finally end up with a set of coordinates, XY coordinates, of the mitosis locations. And this would overall be our mitosis detection approach. Okay, so first step, like we said, we'll kind of go through each piece. Pre-process. So like we said, the part on the left is what the actual piece of tissue would look like. We happen to have a piece in the middle now, which is a high-powered field. It's a piece of tissue without any extraneous background, so we don't have to worry about that. And we're going to cut that up into patches. And so if we set our original images are maybe 2,000 by 2,000 pixels or 5,000 by 5,000, that's too large generally for the types of models we'd like to run and the amount of processing power and memory that we tend to have. So our patch size is going to be 64 by 64. We could do slightly larger. We'll find that the cells are about 30 to 60 pixels in diameter. And so this is roughly an okay size to try, and larger size may not be necessary. Nonetheless, that's what we're using at this point. So it seems very simple right here. There's an interesting thing, though, that if you're going to cut it, if you're going to take this approach, I guess I should just stop in case anyone's familiar with other approaches to these types of problems. There do exist algorithms such as RCNN or YOLO, or perhaps if we wanted to rebrand this as an instant segmentation problem, we could use mask RCNN. That could allow us to maybe perhaps approach this problem directly. But nonetheless, that's for future exploration. But in this problem, if we like to take this approach where we're cutting up a high-powered field into patches, and then we're going to make predictions as to whether each patch contains a mitosis or not, then how we cut it into patches is important. And would find that if we just take a patch and then we slide over and take the next patch over to the right, and then the next patch to the right, completely non-overlapping, we could run the risk of missing a mitosis. So mitosis could be in the center of two patches. So we can say, okay, let's just overlap about halfway, and that could be enough. But we could still get cases where the patches or the mitoses are towards the left or right-hand side of a patch. So we could end up with an arbitrary overlap. And then the limit, we could go to a single pixel. Just slide over by 1 pixel, take a patch, 1 pixel, take a patch, and so on. But we'd find that with the number of images we have and the size of them, that may yield too many patches to actually be trainable or feasible with the amount of processing power that we have. So this will come up as a problem that we have to think about more deeply. Okay, so back to our fun diagram. So that's our pre-processing stage. And the way we do it currently, and there's other possible ways, is we do run that as one batch job, run it, send it out, and save it to some kind of disk. And keeping track of the science, that is something we want to keep track of, is what data set is this, how did I create it, and why did I create it? So training. So this is the fun, super fun part, right? Take our patches. So we've cut this up. Patch should be roughly contain a single cell, ideally, something like that. And we know for any given patch whether or not that patch contains a mitosis or does not contain a mitosis. So at this point, we have a binary problem, yes or no, even though the overall problem is to take a big piece of tissue and output coordinates. Cut it up into patches, the subpart becomes a binary classification problem. So we can take our patch, can train a model and predict yes or no. So 0, 1 mathematically. So for the training, I'll come back to augmentation, but for the training, one of the thoughts here is to use what we would call fine-tuning or pre-trained models. And the thought here, if you're not familiar with this, is that there exist types of deep learning approaches to image problems, in which we have very large models. Typically, we use many layers or many compositions of convolution functions and other functions that are very applicable to images, particularly to the idea that images have spatial orientation and spatial invariance, meaning that a cell, in this case, the cell could be perfectly in the center, or it could be slightly to the left, or slightly to the bottom right, and that doesn't matter. So we would like to be able to find it regardless. And so these kind of convolutional neural networks are very ideal for this type of problem. But in practice, for the research we've seen for image classification in academia, particularly on the ImageNet dataset, a lot of the models that have been very successful are very large. And the ImageNet dataset is quite large. And so one of the approaches towards applying that to a maybe perhaps smaller dataset is to take one of these models that's been trained on these very large datasets, such as ImageNet, and then you manipulate it such that you can apply it to your personal problem, and then keep training on top of that model that was already trained. And so what it looks like in practice is you would take, for example, a VGG or a certain ResNet, and these are just models that have been produced in academia research, usually on the ImageNet dataset, and they may be set up to take in some images. The size actually doesn't matter once we make some manipulations. And they will produce, in the end, some classification. And so ImageNet has 1,000 classes. So these models, the very last function, that's what we're kind of seeing, is the very last piece here or here. The very last function will be set up to produce 1,000 numbers. And particularly, it'll be a normalized set of probabilities as to which category this image is. So clearly, for this problem, those 1,000, like the cats and dogs and stuff, don't really apply. But the rest of the model might have learned certain types of features of images in general that might be generally applicable. So the thought is earlier on in a model, you might have very low-level features such as edges or curves and such things that you could use for other types of data. So what we can do is we can take off that final function, just rip it off, the function that yields, it's just a matrix multiplication that yields those 1,000 numbers. We rip that off, and we can apply our own function on top. And this function would just yield a single number followed by a sigmoid, which would yield us a single value that we can interpret as a probability between 0 and 1. We could use that as a probability, roughly, of whether or not this yes contains a mitosis or no does not contain a mitosis. So the idea is most of the function stays the same, except for this last little piece, and we put it on there. So we can do that with ResNet or VGG, and then now we have a model that's been pre-trained except for this new function we've put on the end. And so when we do that, we'd like to train just that new function at the end. So since it's random, we'd like to train it. And then we can slowly continue training the rest of the model. We say slowly because ImageNet's very large. This data set may be relatively smaller. But we'd like, perhaps, in this hypothesis, to use some of these models that we pre-trained. So it's a very interesting concept. We can talk more about it later. But nonetheless, we could make use of a model that's been trained previously. One of the things that's very nice as well for training models is this idea of augmentation. So the thought here is that if we keep it relevant to our current problem, there are many possible images that you could see for our problem. And more generally, there's many possible types of observations you could make. We don't have every piece of tissue ever made in the entire world. We just have the data set that we have. And so the thought is that we'd like to have every piece that we have in the world. So what we can do, though, to kind of supplement the fact that we don't, is add this idea of augmentation. And that looks like is we take our labeled patches, and we apply some random perturbations to those patches. So this could be things such as rotating it slightly, or flipping it, or changing the color just slightly. All things that could intuitively make sense, given that the physician could have placed the tissue slightly sideways, or on the other side, or upside down on the piece of tissue, and it wouldn't matter. Nonetheless, it still would have a cellular mitosis located somewhere. And the color, if you pour more or less stain, it may become more pink or more blue, and it still doesn't really matter. But nonetheless, those things could happen. And so the data set that we might go to use this model on in the future for the physician could look slightly different than the data that we trained on. So by using this idea of augmentation, where we add these random changes, we're hopefully training the model to be more robust and to generalize to more data than we currently have observed. So it's a very interesting concept. The papers used augmentation in terms of rotations and flips. They did not use color augmentation, which has been effective in the research community. So it's something that we've been trying as part of our hypothesis. So that's training. There's more pieces we'll talk about here in just a second of how we actually optimize that. So this is the augmentation a little bit more formally. So like I said, you add noise to it, and it artificially inflates the data set. But on the left here, there's little hints of more mathematics. We could talk about all that like I just had in that brief paragraph I just gave, or we could succinctly describe this as the probability of y, so the probability of whether or not it's mitosis, given x, our image, and noise. So that's those random changes we're making. So that's a nice way we can describe this process using probability theory. So there's a link at the bottom. So like we said, this is an open source project. It's all out there. So if you're interested, you can follow along. I've put the exact line numbers. So please, if you're interested in looking at this to apply it to your own problem, feel free. Or if you'd like to jump in and contribute and work on this problem with us, please. We'd love that. So the models, like we said, we have VGG 16s, ResNet 50s. Those are the specifics. There exist other types of VGG models. These are just models that came out in a certain paper with a certain name. Nonetheless, they just have functions within them. But by having a name, they're easier to describe and talk about. Otherwise, we have also experimented with using a custom version of a ResNet. So this is not a pre-trained model. It's a much smaller model. But it's just an interesting thing as a different hypothesis to compare experimentally against the pre-trained versions. Once again, there's links at the bottom. You can look at how we've defined these models, particularly if you're interested in mechanics of how you rip off the final function. The top link will talk about VGG, and the middle link will talk about ResNet 50, and that's using the Keras API within TensorFlow, so tf.keras. And it will show how you pull in a pre-trained model and add your own function at the end. Okay, so for the loss. So you have this model described, right? You need some type of function or evaluation function that you're optimizing. And so in machine learning, we call that the loss. And this is a binary classification problem. And so keeping it in line with this idea of probability theory, there exists a type of probability distribution called a Bernoulli distribution that describes processes that are binary in nature, so yes or no. And so we can take a Bernoulli distribution, we can take the negative log likelihood of the probability mass function for Bernoulli, and we'll end up with a loss function called the logistic loss function commonly, or sometimes the sigmoid or binary cross entropy. But nonetheless, this is the loss function we'll use, and the idea is our model will make some output prediction. Formally, that prediction actually parameterizes this Bernoulli, but nonetheless, it's a prediction. We have an observed prediction, or observed value, whether or not this piece of tissue, or particularly this patch of the tissue, has mitosis or not. So we have a yes or no observation. We have a probability from the model, and the loss function will give us some type of level of evaluation for that. And since it's just a function, this is how we can use calculus and go back in and compute derivatives of this loss with respect to each parameter in our model. And that will just basically give us a rough idea of how important that model, that parameter was, and we can make changes to it. Once again, there's line numbers, so we can look at that. So then it's optimizers. So once you've defined this model and you've got this loss function, you understand how to get the derivatives for it, then you can optimize. And there exist several different optimizers. Basically, the idea is they use derivatives, and if you've got a derivative of this loss function with respect to a parameter, then you can make a slight change to that parameter in the opposite direction of the derivative, and that will, in general, make that function more likely to give you the correct observed value next time. So we use stochastic gradient descent in one case, and that's where a lot of these optimizers are based upon, but it's the idea of doing that gradient descent, but with small batches at a time, rather than the entire data set. For pre-trained models, this is kind of what it looks like, where we have, once we said, we take the existing model, we rip off the end and place our new function at the very end of it, So we can call that new end function classifier, but it doesn't really matter how we call it. But we said we don't want to, that's random. It starts out random, yet the rest of the model is pre-trained. We don't want to destroy the rest of the model. So we can start by training just that final function first, all by itself. And so we can use any optimizer, but the Atom optimizer tends to be very nice for very fast optimizations in the stochastic realm. So we train just that piece, and then once we feel comfortable that that's converged as far as it's going to go, then we can start fine-tuning the rest of the model. And all that really means is that you just slowly start adding more and more functions, starting from the end of your model, going back towards the beginning, into your optimization step. And for that, for transfer learning, we'd like to use a much slower optimizer. And slow here just really means that we can control the rate at which we make changes to the parameters. So formally, we use stochastic gradient descent with a Nesterov momentum. So once again, you can look at links here and see specifics at what this looks like. But in general, overall, you can track this and look at it and see what is my loss or what is my F1 evaluation. And that will give you some understanding of how many functions to continue fine-tuning. Where the idea here is you don't want to accidentally overfit to your data set. So if you're using these very large models, there's a potential they could just memorize your data set. And not formally memorize, but in general, they could get too specific for your data set and have trouble generalizing to a new data set. But you also don't want them to underfit and not be able to make good predictions anyway. So you're trying to make that trade-off, and formally that's this idea of bias variance trade-off. So this is a fun application or fun way to actually work on these types of problems, but use big models when you maybe don't have large data sets in comparison. Now for the custom model, though, that we made that does not have pre-trained weights or anything, we can just pick one optimizer and train the whole thing at once. And so specifically, we use Atom. We could use other ones, but Atom tends to give faster results in this kind of stochastic realm. And there's line numbers as well for the custom resonant, and it's just a bit smaller than the existing resonance. All right, so next piece is metrics. So kind of going back to this idea of science and that you'd like to be able to understand and keep track of your experiments as you're running them and be able to evaluate one experiment against another one. Having the model ready, having the loss function, having the optimizers, having all the math is great. But if you don't know which one's doing better, you'll have trouble actually gauging which of your experiments are better, or more generally, which of your hypotheses is more correct. So you can track things like the loss, of course, which we talked about, the F1 score, which is our final evaluation metric that we're actually interested in. But there's also, we can track a few other pieces. So we said F1 score is a harmonic mean of other values. And so we could track those other values, which are specifically positive predictive value and sensitivity, separately. So we can understand if our F1 score is low, why? Is it because we're just not making any predictions at all? Or are we saying that everything is a mitosis? So those are two different types of cases, and being able to track the metrics will let you be able to explore that and know where to go next and what things to test next. Whereas perhaps if you don't have those and you just saw your F1s low, you're kind of more guessing as to what to approach next. Accuracy in this case is kind of useless. We have very few mitoses and a lot of non-mitose locations. So very trivially, we can get 99.9% accuracy, which looks great. So that's the interesting thing to keep in mind is if you have a severe class imbalance here meaning that in binary classification problem, you have very few of one class and very many of the other. So we have very few mitoses, very many non-mitoses. Accuracy does not become useful, and that's why you want to use F1 scores. All right, then. I guess it was just that bad, right? All right, so we're back. That was fun. All right, so you have metrics. We have a few more slides, maybe 10 more we'll go through. So one thing you want to do here too is you have these metrics, but you do want to compute them for both your training data set and validation data sets. So that's one thing we didn't talk about yet, which is more generally for a machine learning problem, you have a data set that you've observed. But you'd like to know, will it do well in the future? And so one way you can kind of approximate that is by splitting your data set into two pieces. Generally, we'd call that the training and validation data sets. A very large training portion and a very small validation portion. You train on the training one, and you periodically evaluate your model on this validation data set. And you can make some choices based on this validation data set, such as which models to work on next, and such things, but that's important to track. Won't talk about too much, but in talking about science and experimentation, having some way to track these, especially in real time, is quite useful. I use TensorBoard, lets you see it in real time, which is great if experiments are running for multiple days. Maybe not as useful if they're just run in 5 minutes, say. But for a lot of these deep learning models, they take several hours or several days to run. Training loop, very self-explanatory. Take all the math, everything we've talked about, and just run it over and over. Tracking things and paying attention until you feel like your model is either overfitting or you've reached some level of success. And so that brings us back to this piece. And so the final piece, this overall thing, is, or I guess one thing is this model bootstrapped over sampling. We'll kind of go through this quickly. The idea is the very first time we talked about earlier that how you sample your patches could be very difficult, meaning you could miss patches or you could have too much data. And more generally, so that means you'll have to kind of sample patches because you can't take all of the data. And since there's very few mitoses, and there's very many locations that don't have mitoses, how you sample it could affect your training. And most likely the very difficult patches will be the ones of where you have a normal cell in the center that's not undergoing mitosis, as opposed to a cell that's just, or a patch that's just in between two cells and doesn't have any cellular components at all. That would be a very easy one. And it's more likely that you'll have patches of places in between cells than you will of those more difficult cells or difficult locations near a mitosis. And so one thing we can do is we can take an initial trained model, go back into the pre-processing step, and for every patch that we might consider, we can run it through the model and ask the model what its prediction was. And if the model predicts that that location is definitely a mitosis, and it's absolutely not, because we've observed and we know it's not, then we could conclude that that is a difficult patch, and we will sample that at a higher rate than we'll sample other ones. So it's a way for us to figure out which areas are difficult without having to have that explicitly annotated by a pathologist. So we could talk more about that, but it's an interesting concept, and there exists data or code for it. Final piece is the prediction, and this is it. So once you've got this model trained, you've gone back in, you've got this new data set that you think is more difficult, that'll help you train a better model next, then you're left with a model. And a model that, given a patch, can produce a binary classification, yes or no. But the overall problem was actually to predict coordinate locations given the overall piece of tissue. And so that comes up for the, that's where the prediction part of the algorithm comes into play. For that, we can take our model and we can cut up the original image into patches, as many patches, every single place, or we can decide which patches to sample, which we can talk about offline. Take our model, predict for those places, and then we'd have prediction for each patch. And we won't talk about too much, but if we add augmentation during training, where we're adding those random perturbations, we can do the corollary during prediction, where for every patch that we have, we'd like to make a prediction. We can make several random variants of that patch, make predictions for each random variant, and then average over that. And formally, we're actually still injecting noise and then integrating out the noise. And so if you think about it more probabilistically, very interesting idea. Takes a very long time, but nonetheless, it's effective. Once you have the final predictions, then you can do other things where, like we said, where you sample patches could be very difficult. And so you could end up with clusters of predictions in certain locations. And since we will be docked heavily by making an incorrect prediction, then a cluster of incorrect predictions will all be incorrect and will affect us individually. So we'd like to be able to actually just make one prediction for any cluster of predictions that we happen to make. And so we can do post algorithms to actually find clusters of predictions and yield a single prediction, which hopefully it won't affect us for positive areas since they give us leeway. But for any negative area, it'll help us from having to make all those incorrect predictions. So there exist two different algorithms. We won't talk about them too much. One of them, though, is a smoothing algorithm, which came from the original paper that we first referenced. And another one's a clustering algorithm. It's more self-explanatory. We can certainly talk about it afterward, though. And then the final step is just, if you do any of these, is to make the final detection, pull out all these locations, turn them into coordinates, and then you're left with a CSV file of XY coordinates of your mitoses. So overall, take a piece of tissue, pull out locations and patches, run it through a model, go back in, generate a more difficult data set based on your first model, train a new model, run it through predictions, perhaps using marginalization if you used augmentation during training and you can afford the computational time. Then for each patch, you yield out predictions for the overall high-powered field. You can cluster any or find clusters of predictions and yield a single prediction and eventually create a CSV file of XY coordinates. And that's our approach. So with that, open for any questions, or we can conclude it now.
Okay, let's take 2 questions.
Okay, I have 2 questions, but we'll just count it as one. So, the first one's fast. How did your results compare to the winner of the challenge?
Yeah, so that's a good question. So we are still working on it. We're close. We think we're close to within the first few spots on the challenge, but we'll see. We haven't submitted formally yet. The competition is over at this point, but they are allowing for post-competition submissions. And once again, we were interested in it because there exists no previous open source approaches to this problem. There exist papers, but not open source approaches. So hopefully we'll be able to submit very soon, and we'll see. But it'll be very interesting to be able to compare our approach versus the papers, which had a few extra things, such as color augmentation, marginalization, et cetera. But it's a good question. I'd love to share, maybe perhaps next time.
And the only other question was, if you actually wanted to deploy this in the real world, there's additional things you'd want to add to just the core algorithm. For example, you might want to see if a sample handed you at production time fell outside the distribution of samples that you used in the training set. Do you think there's things you learned in the process that would help you with that part of the problem, or is that just beyond the scope of what you're thinking about?
Yeah, so that's a big problem in general, is like generalizability and how you can detect that. I think that's a broader discussion because that's difficult itself. Perhaps you could try to predict whether or not that does fall. You could actually formally make an algorithm to predict whether or not a given input is similar to a given input from your data set. But that's a very big problem in machine learning in general, but a good one to ask about.
One more question.
I was kind of wondering if you have an idea of how much running your training would cost in terms of, on a cloud, or how many GPUs or something. There are things that Google or IBM can do that just your average programmer can't because they're prohibitively expensive to get the same results. And kind of the reason I'm asking is kind of a second question related to that is, let's say you have video where you're doing an endoscope or something like that. Any recommendations on optimizing that versus just grabbing every few frames or something to kind of deal with that, huge volume of data you'd have from that?
No, so these are good questions as well. And this goes back to this kind of ongoing sub-discussion throughout the talk, which is how you sample patches is a big issue. Because you can imagine if you took them completely side by side, then you'd have a smaller data set, but you run the risk of missing mitoses. We can fix that during training. Perhaps we know where the mitoses are, but at prediction time, we don't know where things are. But if we take a very, very large number of patches, so slide over by 1 pixel or so, it becomes a much larger problem. And so these is a good trade-off. For deep learning types of models and approaches, for training them, typically you do need a GPU to train on. We'll train these. So I'll give an example. So training a single model on 1 GPU could take, for some of the models we're doing and some of the approaches, could take 10 to 20 hours to train. So that's approachable as an individual. However, prediction time is very interesting because that can be very costly or not, depending, once again, on how you sample patches from the data set for this approach. Because at prediction time, once again, you have some piece of tissue and you've got an image of it, but your model is, and your whole algorithm is set up for patches. And so the way you sample patches at prediction time is also a big deal. And there, you really don't know where the mitoses are. Even though at training time, you do know the mitoses, so you could sample side by side or even greater, but sample particularly explicitly the mitoses. Prediction time, you don't know where that. And so how you sample is very difficult. And that affects how much computation time. The more patches you have to sample, the higher your time it takes to predict. So for this problem, it's the training and prediction are very difficult. For video, it's an interesting question. Mathematically, typically right now, we tend to approach those. For this type of approach, you'd probably approach it still by just cutting frames and putting it on there. For other types of problems, you could approach that as a sequential type of data sets. So you have images over time, basically, is what a video is. For this problem, probably you could do it by just cutting frames and tailoring that towards the amount of computation you have. These are good questions, and it also depends on what type of device are you running. Are you running locally on some very small device? Are you going to try to stream it to some cluster? You don't need a GPU at prediction time, though, if you're doing it live. If you have a very large number, perhaps it could be helpful, very large batch. But for single cases, you probably don't need a GPU. As for exact cost, once again, it kind of depends. And you could kind of gauge GPU hours based on how much that costs at a certain time.
Okay, let's thank Mike and our other speakers.
And just one final plug, we are hiring, so if you're interested in working on these types of problems, please come talk to me. Thank you.
Where's your work?